The purpose of this project is to produce a cogeneration system for an engine which we have built that uses the waste heat to produce work. For our design, we chose to build a Stirling engine and use copper coils to collect the wasted heat through the pressure vessel. A Stirling engine basically produces work by a heat gradient, where an ethanol candle heats the base and ice is placed on top of the pressure vessel. The pressure produced inside of this vessel causes the piston to rise, which causes the crankshaft to turn. As the crankshaft turns, it also moves a connecting arm, which pushes cold air into the pressure vessel and causes the piston to move back downwards, and the cycle repeats. The cogeneration system works by coiling copper around the top of the pressure vessel where heat is exhausted through conduction. This heat is used to warm water that is circulating through coils as a form of harnessing the lost energy. The cost of this engine was very modest, using mostly recycled materials such as slim fast cans, pop cans, a balloon, and coat hangers. Materials which needed to be purchased were high temp epoxy, PVC gasket maker, and a PVC elbow. In total, the cost was about $20 for these parts.
This is our first idea here. We put a lot of work into this, and we've experimented with lots of different ideas. We're now considering actually rebuilding the idea because it's generally not turning, and we think we're going to have to follow the original directions from the website down to a T.
Just put our crankshaft extension on. A little bit tedious, but it's epoxied on there on top of our pin. And now we have decided to make our crankshaft supports out of pop cans, gluing the two layers of them together for strength. So that's what we're doing right now, and then hopefully by next meeting we can have most of it together so we can test in a couple of days.
This is our elbow. From here it's a 1/2 inch to a 3/4 inch. What we've done here is basically we've used a Dremel and a knife to shape it to the size of the can here, so that it's easier to fit when we can just apply the PVC or epoxy. Basically right now, yeah, we're just working out the edges so that it'll fit perfectly smooth up against the can.
Was we drilled a 1/4 inch hole into one of the arms to make a hole for the air to go through to the elbow, and then we drilled a, what was it, 3/36 size hole in the top of each of these to fit the hanger wire through, and we use RTV high temp gasket maker to glue it on and made sure that it was sealed around here and used elastics to hold it on. Tomorrow we're going to make sure the seal's complete before we proceed to put on the... You're in the way. This needs to be this way.
The ones on the outside
have to be bent upwards.
Somebody needs to hold
bend it
here
upwards
and here and 4 pliers, so you need a plier.
Using an infrared thermometer, we took temperature readings of the flame, pressure vessel, and coils both before and after the engine was in use. The work produced by the engine can be determined using the RPM of the flywheel. We will perform an energy balance and entropy balance analysis on various parts of the engine. Using this information, we can identify points of inefficiency and find ways to improve the design of the engine.
It's just moving so fast, it's on fire.
It might actually be on fire.
Yeah, it's really smoking.
The benefits of using a Stirling engine are that it has the potential to produce a significant amount of work by spinning the crankshaft. Benefits of using copper coils as a cogeneration system are that it can be easily shaped to fit the size of the can and collect a significant amount of wasted energy, since they have a high contact and surface area. In practical applications, this could be used on a much larger scale, where water circulating through the coils could be heated and used for such things as floor heating.